far we have discussed about exact solutions of Navier-Stokes equation in Cartesian coordinate system, but there are many problems in physics and engineering where other coordinate systems are important, and one such important coordinate system is the cylindrical polar coordinate system. So, we will talk about two such problems very commonly encountered in physics and engineering today, and the first problem is, so example 1, fully developed laminar flow through a circular pipe. This is also called as Hagen-Poiseuille flow. So, we have not yet touched upon what is laminar flow and what is turbulent flow, but classically that is the case that we introduce the Navier-Stokes equation first and then introduce the laminar and turbulent flow in the lectures. So, here we need to give a little bit of a physical understanding that by this we mean that fluid is moving in orderly layered fashion, one layer over the other, and there is no chaotic or random motion in the flow. So that the flow is I mean whatever is the reduced dimensionality of the flow, that is if we consider a unidirectional flow as a fully developed flow, that unidirectional flow concept is preserved. Otherwise if it is a turbulent flow, it is a random chaotic flow, so the unidirectional nature of the flow may not be preserved. So let us assume for simplicity that the pipe is horizontal, but even if the pipe is inclined or vertical, by this time we know that there will be a component of the gravity as a driving pressure gradient. So you can replace the pressure by the static pressure plus the h rho g, which so P plus rho g h, that is called as piezometric pressure, and you can use the piezometric pressure instead of the static pressure to work out the problem if there is a component of gravity in the direction of the flow. So even if it is a horizontal pipe or an inclined pipe, the method of working of the problem is still the same. So let us say that this pipe has a radius of capital R, and the important components coordinates are, see this is the axial coordinate z, this is the radial coordinate r, and there is a theta coordinate. So if you draw the other sectional view, so you have the r direction, the radial direction, and the cross radial direction is called as the theta direction, which is defined by this polar angle theta. Let us say that the flow is fully developed, and if it is a fully developed flow, we can write a simple force balance on an element. So let us say that this is an element of axial element of length dz, and the radial element and the radial location is small r, if the flow is fully developed, all forces on this element are balanced, so that there is no net acceleration. So let us say that let us write all the forces. So let us say that the pressure here is P. So P into pi r square is the force. So here it is P plus this one, and there will be a shear force. This is acting over the periphery of the element. The element is having a surface area of 2 pi r dz. So this is tau into 2 pi r into dz. Okay. This tau is tau at a radial location r. So because all forces are balanced, you can write P into pi r square minus P plus so you will get tau is equal to minus r by 2 this one. So this tau, if it is a Newtonian homogeneous isotropic Newtonian fluid, we can write this remember that being the fully developed flow, the velocity in the z direction, which is Vz, is a function of the transverse coordinate only. This is exactly same like the parallel plate flow problem, only the difference in equation is because of the change in coordinate system, otherwise it is all the same. Why minus? When you write tau is equal to mu du dy, say you write tau is equal to mu du dy, then what is this y? You cannot choose anything as y. This is very very important concept. So this y is, if you have a surface like this y is an outward normal direction to the surface. So here the y coordinate which is normal to the wall is opposite to the small r coordinate, and that is why that has been adjusted with a minus sign here. So then we can write, so this is a function of r only. Now this is a function of z only. How do you know that? You have to refer to the r component of the momentum equation. So that is where full Navier-Stokes equation is required. See, in many books in the undergraduate level, for simplicity the authors show this simple balance and just by magic they write this as dp dz. So this becomes dp dz by referring to the r momentum equation, where because of fully developed flow you have Vr equal to 0, the radial component of velocity equal to 0, and that makes del p del r equal to 0. That is from the r momentum equation, r momentum. So that needs to be carefully considered. It is just like y momentum equation for a parallel plate channel. Referring to that only tells that this is a function of z only, and therefore this becomes dp dz. So this should not be taken as an automatic, and that is why just a simple force balance along the z direction may not be good enough to give a clear picture of this. You also require a force balance along the r direction to tell the complete picture. So with this understanding, so we can also argue that the left hand side is a function of r only and right hand side is a function of z only. So Now each of these so of course it is a function of z only if you bring the r in this side. So you can write this as a separated variable with function of r is equal to a function of z, or in other words in a little bit more mathematical way, an ordinary derivative if you bring r in one side becomes same as a partial derivative, and that is true when each becomes like a constant. So there are many ways of looking into it, but I would say that to convince a student the most important way is the physical way. The physical way is that along the r direction the force balance gives this, okay. Now so you have dvz dr 1 mu by, so sorry okay, so d 1 by r dvz dr is equal to, so 1 by r, or you may write, yes okay, maybe we will write this as 1 by 2 mu dp dz. Let us just write it in this way, so that you have separate function of r and separate function of z. Now if you integrate it, so this let us say is a constant, is c. So dvz dr is equal to, or dvz is equal to c r dr. So if you integrate it, vz is equal to c r square by 2 plus c1. Here you may have some students having a dilemma that the velocity dependence in the Navier-Stokes equation is a second order dependence. So but only one constant is appearing, that means you just can use one boundary condition to find out the velocity profile. So where is the need of the other boundary condition gone? The need of the other boundary condition is hidden in this analysis. So here we have assumed a symmetry with respect to the center line, and that means you have implicitly assumed that at r equal to 0 dvz dr equal to 0, okay, otherwise you cannot write this symmetric force balance. So you have vz is equal to this. So symmetry at the center line we have already used, so only one boundary condition that we is left is at small r is equal to capital R, vz is equal to 0. So at small r is equal to capital R, vz is equal to 0, that means C1 is equal to minus c r square by 2, okay. So you have vz is equal to c by 2 small r square minus capital R square, again a parabolic velocity profile. Now you can find out the average velocity and express this c in terms of the average velocity. So if you do that, so let us calculate the average velocity, v average vz into 2 pi r dr by pi r square, okay. So c by 2 into r square minus r square into 2 pi r dr okay. So then this 2 and this 2 gets cancelled, this pi and this pi gets cancelled, c this is r cube dr, that is r4 by 4, and minus r dr is r square by 2 and r square by 2. So c r4 into 1/4 minus half by r square. So minus c r square by 4, right. So, if you substitute C minus V average into 4 by R square. So, you will get Vz by V average is equal to 2 into 1 minus, okay. So, this is the velocity profile in terms of the average velocity for the Hagen-Poiseuille flow. So, we can also calculate the pressure drop, because as an engineer you know the velocity profile is important, no doubt about it, but what is fundamentally required is that if you want to drive a flow, how much pumping power would you require, because that is the pumping power that is required to overcome the viscous resistance, and without that the fluid cannot flow continuously through the pipe. So, your application does not work. So, to get a clue of that, this C, that is 1 by 2 mu dP dz is equal to minus 4 V average by R square, okay. Now, this dP dz you can write minus Hf rho g by L, where this Hf is called as head loss due to fluid friction, okay. So, this is basically a length equivalent of energy. So, this is the energy that is lost to overcome friction, because it is a loss of energy, this is given by a minus sign, okay. So, then you can write Hf is equal to 8 mu V average, sorry, so Hf rho g by mu L is equal to 8 V average by R square. So, Hf is 8 mu V average L by rho g R square, and because V average is the volume flow rate by pi R square. So, this you can also write as why this is important is because it is not the average velocity that you measure, but the volume flow rate that you measure, and normally in engineering it is a diameter instead of the radius that we write in terms of. So, this becomes 128 mu q L by rho g pi d to the power 4. So, this is called as the Hagen-Poiseuille equation. Head loss due to fluid friction in fully developed flow through circular pipe. There is a I here, okay. So, you can see that for a given flow rate, head loss is inversely proportional to the fourth power of the diameter of the pipe. So, if you reduce the diameter of the pipe, it requires huge pumping power to drive the flow, and that is why in micro scale flow you have to use other forces like surface tension force, electrical force, etc. to drive a flow in many practical circumstances, because to maintain a particular flow rate, if you make the diameter smaller and smaller, the head loss becomes larger and larger, and huge pumping power is required. Now, there are two important friction factors in engineering. One is a Darcy friction factor. This is given by the Darcy-Weisbach formula Hf is equal to FL by D V square by V average square by 2G. This is valid for both laminar and turbulent flow. For a fully developed laminar flow, this F can be calculated by equating this with this one, and you will get F is equal to 64 by Reynolds number if you calculate this, where D is the diameter of the pipe. This is called as Darcy friction factor. There is another friction factor or friction coefficient which is called as fanning friction coefficient. This is Cf tau wall by half rho V average square. So, because the wall shear stress is related to the pressure gradient from which this Hf has come, so one is actually the 4 times the other. So, one is 16 by Reynolds number, another is 64 by Reynolds number. So, that can be easily shown, and I leave it on you as an exercise. The other problem that we will consider today is a very interesting problem, which is a flow between two concentric rotating cylinders. So, let us say that there are two cylinders of radii R1 and R2. So, this is example 2. This is called as Taylor-Couette flow. So, if you have two cylinders like this, concentric not eccentric, with radii R1 and R2, they are rotating with angular velocity omega 1 and omega 2, and the gap between the two cylinders is filled up with a fluid. Here, if omega 1 is different from omega 2, there is a shear which acts on the fluid. If the gap is very small, this is equivalent to a plane Couette flow, where you have two parallel plates, one plate is moving relative to the other, and this velocity is maybe omega 1 minus omega 2 into the difference in the radial coordinate, and let us say this is u naught and the gap is h. So, if the gap h is very small, the curvature of this may be neglected. So, this is like a flow between two parallel plates, one plate is moved relative to the other. This is a classical shear driven flow, and this is actually encountered in a more realistic way in this kind of a physical environment. I will give you two examples. One is, if you have a shaft and if you have a bearing, then there is a fluid lubricating oil that separates the shaft and the bearing to avoid metal to metal contact, and there is a power required to rotate the shaft. So, it is important to know that. On a different note, this is a configuration which is used commonly to measure the viscosity of an unknown fluid, which is kept here. That is, this arrangement is called as rotating cylinder viscometer. So, this is a classical way of measuring the viscosity of an unknown fluid, because if you measure the torque and the power which is required to drive one cylinder relative to the other, that expression will have viscosity as a parameter. So, from that you can measure the viscosity. So, with this little bit of motivation, I will use the cylindrical coordinate Navier-Stokes equation, and because we have already discussed the Navier-Stokes equation, so I will straight away get into the different equations without referring to the physical basis. So, the continuity equation So, just a minute. Okay. So, again what I am telling you is that you know, this particular writing of the Navier-Stokes equation and the continuity equation in r theta z coordinate system is a little bit of a tedious job. Never encourage your students to memorize these equations. You do not make them champions by memorizing this. The important objective of this lesson is to see that how they can apply those equations to solve this problem. So, never enforce them to remember this equation. So, in this case because of, so there is v theta, but v theta is not a function of theta. So, this is 0. We assume that the cylinder is infinitely long, so that there is negligible gradient. All these logics have to be put properly, and therefore r Vr is not a function of r, and from the continuity equation therefore we get Vr is equal to 0, because Vr is equal to 0 at some radius r1 and r2. Therefore, Vr is equal to 0 for all r. Then we will consider the r momentum. So, these are long equations, let me write one after the other. These equations are so long, you know, even if you write by looking into the equations, there is a chance that you make some mistake or the other. So, one need to write this very carefully. Okay. So, now we will consider various terms. So, Vr is equal to 0, also it is steady flow. Vr 0 means all these things are gone, but V theta is not 0. This is r, right? V theta square by r, right. Br is not there, this all Vr 0, Vr 0, V theta is not a function of theta and Vr is 0. So, the conclusion of r momentum is del P del r is equal to rho V theta square by r. Okay. Then let us write the other momentum equations. Because the space in the board is limited, we have to, you know, erase one equation after the other. So, next we will consider the z momentum. Okay. So, first of all, it is this equation is expected to be redundant because v theta is the predominant direction component of velocity, but let us just see if something was there. For example, r momentum, out of nothing we got an equation for pressure gradient. So, here all these are 0, this is 0 because Vr is 0, this is 0. So, please encourage your students to, whatever terms are 0, you may give a short question like this, why is this term 0. So, this term is 0 not because of this, but because of Vr is equal to 0. So, then this is 0 because it is steady flow, this is 0 because theta symmetry, this is 0 because there is no gradient along the z direction, there is no body force along z. Then here you have so Vz, so this Vz is not a function of theta, Vz is not there because it is a v theta, that is the velocity component, and so this also becomes 0. So, with all this you are left with just del p del z equal to 0. Okay. So, you can have a physical Vz by complicating this problem by pulling one of the cylinders axially. Sometimes we give this as a problem to students in the exam. So, this problem complicated by a cylinder being pulled in the axial direction, then Vz will be there, at least then the students should not write these terms as 0 and there will be a z momentum importance. Finally, we will write the theta momentum. We have not yet written the theta momentum, right. So, we will write the theta momentum. Okay. So, now we will just quickly see which terms are 0. This is 0 because it is steady flow, this is 0 because Vr is equal to 0, this is 0 because V theta is not a function of r, this is 0 because V theta is not a function of z, V theta is not a function of theta, this is 0 because V theta is not a function of z, this is 0 because Vr is equal to 0. There is no body force along theta, there is theta symmetry with for pressure, and V theta is not a function of theta, this is 0, Vr is equal to 0 and V theta is not a function of z, so this is 0. So, you are left with only this term, let us write that. So, del r of 1 by r del del r of r v theta, this is equal to 0, right. So, this because v theta is a function of r only, this you can just write in terms of ordinary derivative. So, that means 1 by r ddr of r v theta is equal to C1. So, if you integrate it, d of r v theta is equal to C1 r dr, that means r v theta is equal to C1 r square by 2 plus C2, and if you integrate it once more, v theta is, so v theta will be C1 by 2 r, simplification not integration once more, plus C2 by r. So, finally the velocity becomes the form v is equal to ar plus b by r, okay, where a and b are two constants. How do you calculate these constants? V theta is equal to omega 1 r1 at r is equal to r1, the boundary condition, and v theta is equal to omega 2 r2 at r is equal to r2, okay. I will talk about an interesting problem where there is only one cylinder rotating in an infinite fluid, that means there is no omega 2 and you have to have v theta is finite at r tends to infinity. So, example, one cylinder rotating in an infinite fluid. So, v theta has to be finite at r tends to infinity. So, if there is a cylinder or a sphere in an infinite fluid, this is a matching boundary condition that you need to satisfy, okay. So, if you need to satisfy this matching boundary condition, then you must have a is equal to 0, otherwise at r tends to infinity this will be infinity. So, v theta in that case is b by r, where b is determined by v theta is equal to omega 1 r1 at r is equal to r1. This is the classical free vortex flow, right. So, now if you calculate the tau r theta, so tau r theta is tau r theta expression is there, okay. Tau r theta, this is mu r del del r of v theta by r plus 1 by r del v r del theta. So, I am not going into the algebra, but if you calculate it, this will not be equal to 0. Interestingly, what is the viscous stress per unit volume? This is, or viscous force per unit volume, this is viscous stress. This is volumetric viscous force. What is this? So, we have this vector identity this we have used earlier. So, here because it is an irrotational flow free vortex, so this is 0 null vector. If it is incompressible flow, so this is also 0 only for incompressible flow, remember. So, if this is 0, that means this becomes 0 for incompressible flow. So, this is a non-intuitive physical condition where the shear stress or the viscous stress is not 0, but viscous force per unit volume is 0, because local shear stress may not be 0, but integrated it over a volume, the net effect is that there is no net viscous force. So that is possible provided we are coming to the conclusion, we are getting into the consideration that it is incompressible flow. If it is not incompressible flow, this and this equality does not work. Okay. So to summarize, in this lecture we have discussed about the uses of Navier-Stokes equation in cylindrical polar coordinate through two important examples. In the next lecture we will discuss about some unsteady flow solutions, exact solutions of Navier-Stokes equation. Thank you.